Hello, everyone. I'm in the PC room. I didn't know if I told you that someone could have come in person. I didn't know. There is nobody, but just in case, I will say here. So if someone wants to pop in, I don't remember if we agreed that it could have been in person or not, this revision. But let's wait a couple of extra minutes and see if someone shows up, someone else. How are you guys?
Okay, thank you.
Well, since I'm going to record, I think I'll start straight away, because let's say that I'm not going to keep you long. I will just like to revise the main parts of the course that you've done with me. So you will see in the next slides, which are available on Canvas anyway. So my aim is not to stay longer than a half hour, but that depends. So especially because in the final slides on the advanced retrosynthesis are actually the same one that I put on the video, which is just about the strategy. So I think that video hopefully should speak for itself. So in case you want to revise the strategy for retrosynthesis, actually I prefer to watch the video over watching the general revisions. But we will talk briefly about that part too. So allow me to share my screen. I don't know what's going on here. No, sorry, I'll start again. Can you see my screen with revisions? Please, someone let me know. Yes, so you do. Okay. So general revisions on this part. So you started with me, and we've done at the very beginning three main, we touched three main topics, three main areas. We started with the cross-coupling reactions. Then we carried on with the pericyclic reactions, and then with the spectroscopy. So what I called spectroscopic identification of organic compounds. Remember that all these parts will be present at the exam, including, of course, the last part in retrosynthesis. But you will have retrosynthesis both with me and with Marcella. So I take for granted that you know that retrosynthesis is going to be a big chunk of your exam. But from my side, also cross-coupling pericyclic reactions, and especially this one of the long questions, as I told you from the very start, one of the large questions, the 25 marks one, is going to be the spectroscopic one. So be careful and revise those. So let's start with the cross-coupling reactions. Just to see briefly what we have done. We just seen the main catalytic cycles that usually is involved in this kind of catalytic reactions. We explain some parts depending on the different cross-coupling reactions. We explained the roles of the oxidative additions and reductive eliminations. Also with the migratory insertion, which happens very often. I'm not sure I'm going to put it at exam, but please revise it because it might be very useful. We saw the versatility of the palladium. Remember that not only palladium is good for these cross-coupling reactions. Actually, if you go for literature or papers and other books, you will see there is a huge variety of transition metals. From my point of view, normally I will use a transition metal. Palladium could be one of them. So for the retrosynthesis point of view, for instance, if you just have to do a cross-coupling reaction and you tell me I will use a palladium 0, it will work. If it's a specific question on some parts of the cross-coupling reactions, please have a good look at the questions and have a good look at the role of the transition metal. But most likely, you'll always find palladium. We saw different reactions, cross-coupling reactions that might be very useful for retrosynthesis too. The Heck is one of them. Suzuki, Negishi, Sonogashira, Stella, you name them. I don't want you to remember all the names, but it will be really nice if, for instance, you're using them in retrosynthesis or in forward synthesis. I think that most of you noticed already on the big workshop that Sonogashira was one of them. When there is a triple bond, Sonogashira is always a good choice, especially if that Sonogashira coupling actually breaks the reaction in terms of retrosynthesis. But have a good look at Suzuki couplings as well and all the rest of the couplings. So you notice they are quite useful in synthesis. We saw the role of the transition metal complexes, like I was telling you before, but let's, generally speaking, let's say that they all work more or less in the same way. So whatever is the transition metal, could be palladium, it could be, very often it could be nickel, it could be copper, that depends. But the retrodonation, because of the different ligands, they always work kind of in the same way. So be careful if we are talking about a question on proper cross-coupling reaction, or if you're more generally speaking, if you're using for retrosynthesis. Okay, so let's revise all these kind of methods and all these kind of oxidative additions, reductive eliminations. Sometimes we do migratory insertion, especially be careful on the transmetallation step. That could be very useful. And that depends from the transition transmetallation step, that depends the kind of cross-coupling reaction you're using, okay? This is the typical catalytic cycles. Sometimes we change them a little bit, but the most important parts are the one that we just named. Be very careful again on the transmetallation, because depending on the transmetallation step, you are using one coupling or the other sometimes. For instance, Suzuki uses in the transmetallation step the boronic acid. Remember also how to make boronic acid. That might be very useful for retrosynthesis. Then we saw the pericyclic reactions. So we spent a good 4 hours, as far as I remember, doing pericyclic reactions. They are incredibly useful. You saw them in synthesis and retrosynthesis too. It's very good. This is the only part I will say that on my side, I took care of the stereochemistry too. All the rest of the stereochemistry was normally taken care by Marcella. But on the pericyclic reactions, we noticed that there are some differences compared to the other kind of cyclizations. So since there are these differences, sometimes the stereochemistry is predictable. And if the stereochemistry is predictable, sometimes at the exam, I will ask you, you probably notice on, if you had a look at any past exam, I will probably ask you, what about the stereochemistry? Either to justify the stereochemistry, we saw some exercises in class, or to predict the stereochemistry. And so you have to tell me what product you will obtain and what is the stereochemistry of that product. In order to do that, normally either you take care of the molecular orbitals, or you take care of the different attack. For instance, on the Diels-Alder, we know that it has to be a syn attack, and the stereochemistry is dictated by the syn attack. For some others, remember the Woodward-Hoffman rules. There are tables that can explain it, we will see. But the stereochemistry could be very important for this kind of reactions. Especially remember that there are either thermal pericyclic reaction or photo-induced pericyclic reactions. The stereochemistry is usually inverted one with another. They are very well explained in the videos, and they are very well explained, especially on the Claydon. But I use the Claydon to prepare my slides, so you should follow them more or less in parallel. So to do pericyclic reactions, you normally want to revise, let's say, the typical cycle formations. So these are the typical cycle formations. We saw them in the second year. We saw them in this part. Let's remember the differences between forming different ring sizes, okay? But normally speaking, these are the typical pericyclic reactions. So remember, the typical movement is of 3 arrows. Depending on what the cyclization is, you need to move them in a way or another. Depending on the heat or if it's irradiation, so photoinduced cyclization, you obtain, like you can see in this slide, different stereochemistry. This is very important for the exam. And this is, of course, is very important for the exam because it's very important if you have to do it in the lab, really, because these rules for the pericyclic reactions are quite strict. So there are not many exceptions for the Woodward-Hoffmann rules. There are some because there's plenty of exceptions in chemistry and they can be explained, but normally speaking, I will not give you any exercises at the exam which is ambiguous. So if I'm going to ask you something about these rules, it's absolutely unambiguous. So don't expect having many exceptions. So be careful and remember all these tables, for instance. This is a very small one. And you want to remember if the rotation is this rotatory or conrotatory, depending if the pericyclic reaction is actually thermally induced or photochemically induced. Remember to practice with all these kind of exercises, because only after you practice, you actually remember and you actually make, I will say make your mind up in what the stereochemistry is, but it's like when I tell you on retrosynthesis, don't need to do the mechanisms because I will not ask you the mechanisms. But if you can do the mechanism, I am pretty sure that you know absolutely the outcome of the reaction. So it helps. Sometimes, like I said, at the bottom of the slide, the stereo control is lost during competing radical reactions. But I'll say it again, I will not give you at the exam anything like that. So my exam questions are absolutely unambiguous. We took very good care of the Diels-Solders, especially because we use Diels-Solders more in retrosynthesis and in forward synthesis than other photochemical reactions. So Diels-Solder are more likely. They're very versatile, very useful. They are very forgiving for different functional groups. The only thing you really need to remember is the regioselectivity of Diels-Solder and the fact that the dienes need to have that kind of cis conformation, and the dienophiles must have a good electro-withdrawing group. If you disconnect a reaction, a 6-member ring, and on one side you put on the dienophile an electrodonating group, I am pretty sure it won't work in the lab, so that will be a mistake. So despite sometimes you do the correct arrows movement, it might be a mistake. So be sure that if you're doing a Diels-Solder, the dienophile, so the just double bond, has a good electro-withdrawing group conjugated to it. That's very important, okay? There are other reactions, especially to form, we noticed that we can form 4-member rings, which are, if you consider the normal cyclization rates, the 4-member rings are the most difficult one to form. They're incredibly difficult to form. But if you can do pericyclic reactions well, they can be, I wouldn't say easy because they're never totally easy, but they're doable. So for instance, one of the reaction we have seen is by using this ketene and a double bond, and you can form 4-member rings. They are especially useful if instead of normal ketene, you use, for instance, an isocyanate and you form beta-lactams. It's very useful because beta-lactams are always present in different drugs. And if you want to disconnect the reaction next to the beta-lactam, you can do that using pericyclic reactions. Okay. Also in this case, stereochemistry can be controlled, but let's say that with this kind of pericyclic reactions, controlling the stereochemistry is more difficult than with, for instance, a normal DL solder. We saw in the very last part of the pericyclic reactions, we saw Claisen rearrangements or other sigmatropic rearrangements. Claisen is only one of the most famous ones. So for instance, this one could be useful in terms of retrosynthesis too. But actually, I will say that it's unlikely that you will spot in a retrosynthesis actually a good use of this kind of rearrangements. And it's unlikely that I will put a question which requires absolutely that you must use this kind of rearrangement. It might happen, and I will be very pleased if you can do it. It might happen that you can see in one reaction a possible sigmatropic rearrangement. And if you can do it and it works, I will be double pleased because normally I don't require them. But if you can use them, be creative, but be plausible in retrosynthesis. Okay, so have a look at the mechanisms for these rearrangements. Have a very good look at where the double bond goes, where the double bond migrates, because that's very important on if you really want to use these kind of rearrangements. Is most likely. Well, I wouldn't say most likely because I'm not going to tell you if I put these kind of questions or not, because I would like you to study all the rest too. But whenever I use these kind of reactions, normally I can tell you, either tell me where the new bond is formed, so where the group migrates, or explain sometimes the stereochemistry for other pericyclic reactions. These are the kind of exercises that I put. It's more unlikely that I'm going to use them for retrosynthesis. A good part, and I'm telling you, one of these questions has to be, to me, it's too important that you know how to do spectroscopic identification of organic compounds. You saw that, how useful is that in a lab this year. Sometimes you notice that some of the different reactions, byproducts or minor products that you want to characterize out of a reaction, they have to be characterized by these spectroscopic techniques. So if you want to use spectroscopic techniques, it's absolutely important you practice with these exercises. So we saw FTIR, which probably it was the best known of for you all because you started using FTIR from the first year. A little bit of UVVs. I will say that UVVs is normally good, and you need to tell me at the exam if you're spotting aromatic groups or not. Or instead of aromatic groups, could be conjugated groups. So remember that an aromatic is just different double bonds conjugated one with another. So if you have other double bonds connected to your molecule, which are conjugated, it's very likely that you can spot it on the UV. So not necessarily the UV is good only for aromatics. So keep in mind that. We saw good fragmentation, good exercises in fragmentation with a mass spec. You should know something like that already because of the courses with that. Remember some of the recurrent numbers on mass spec, but especially we use proton and carbon NMR. Proton and carbon, sometimes you can solve your exercise just using the formula, and so the number of unsaturation we will see in a minute, and proton and carbon. But remember for the exam, for the strategy for the exam on these questions, remember, please comment on each spectrum I give you. So if there is something to comment on the FTIR, normally I can number the peaks or I can highlight the peaks that you need to comment on. So please comment on each single technique, because otherwise you might end up losing easy marks. There are two very good books to practice. All my exam questions are actually taken from the field. So here I can see the 5th edition, but there are different other editions. There are so many different, something like over 200 exercises. You can practice quite a lot. All my exercises are there. So if you do them all, you are sure that one of them is going to be at your exam. If you do them all, probably you don't need to remember because you study so much that you will see the molecule even without remembering the exercise. The other book, the Silverstein, is much better for theory. So for instance, it's very good for practicing with a chemical shift of the Mars, fragmentation, mass spec. The field is good for exercises. The Silverstein is really good to learn the technique. These are the routine operations that you need to do to solve the spectroscopic problem. Remember the molecular formula for the degree of unsaturation. This has to be, it's not probably, it has to be the first thing you do. So that calculation of the degree of unsaturation tells you already quite a lot about your molecule. And especially after you cross-checks all the, you do cross-checks of all the different spectra that I'm giving you. If you keep in mind the degree of unsaturation, then it's really helpful. On the FTIR, check for the presence of absence or of different functional groups. Remember that FTIR is very good for determining that a functional group is there or not. Then what is connected to has to be determined by other spectroscopic techniques. We talked a little bit about UV already. Fragmentation on the mass spec really tells you a lot. There are some recurrent numbers that, of course, I keep telling you, there is no need to remember these numbers, but it's really helpful if you do. So fragments are 43, the acylium, and 91, the benzyl, the tropylium ion, which comes from the benzyl group, so an aromatic group and a CH2. And other, 28 loss of CO2, 29 loss of an ethylene group. These kind of numbers are really recurrent. If you remember them, it really helps straight away in your mass spec. Remember also all the fragmentation of halogens. So for instance, bromides have the 2 peaks, almost one tall as the other. Chloride is slightly different. It still has a very recognizable pattern. It's very important for proton and carbon to count all the different number of carbons on the carbon-13. So be sure that you expect and you find the number of carbons, you connect and you cross-check the number of carbons that you have on a spectrum. Try to predict, maybe if, for instance, you have 9 carbons from the molecular formula and you have only 7 peaks, you can expect some symmetry, for instance, because sometimes peaks overlap. Usually I put zooms on some more difficult, let's say, pattern and peaks in proton and carbon. But anyway, use the depth for the carbon to establish if there are CH2s or CH and CH3s. Remember that the quaternary carbons all disappear at the depth. So use the depth and the carbon-13 and again, cross-reference them. If you comment anything between these two, I'm sure it will give you very, very good marks, and because it will give you a very good idea on what your structure is. On the proton, which is probably the most useful one, proton NMR, always comment on number of proton environments, number of protons that you expect, because you have to connect it with the molecular formula. Then you connect with the multiplicity, so shape of the peaks, doublets, triplets, and so on, and the integration. So usually there are not numbers in the integration because they have never been integrated with a software, but there are curves. So use the curves to understand the relative integration between one peak and the other. That's really, really important that you can comment on the integration, because if you have, let's say, 11 protons and you don't count for all the protons on the proton NMR, there will be a mistake. Then, of course, especially if there are zooms on certain peaks, you can check the coupling. So, for instance, if you have CH3 next to a CH2 and you have the typical pattern, a triplet and a quartet, you should mention also that they should be coupled. Even if you cannot really calculate the J coupling, you can see that more or less by eye, this peak should be coupled with this other peak. I'm not gonna use any 2D NMR or 2D, any 2D techniques at the exam. I think they will be probably too difficult, and this is something that also in the lab we don't do it very often. But if you can comment on each one of the techniques and each one of the spectra that I give you at the exam, especially then you should wrap up everything at the end and tell me, because of what I found on this spectrum, of what I found on this other technique, and so on, I think that my molecule is this one. So you give me a good summary on your findings. This is really good. Think about you're doing it in a lab and you want to find out what the structure is of your unknown molecule. Okay, so this is something that you will really use in a lab on a daily basis if you were working in an organic lab. Okay, these are the typical, this is a typical solved exercise. Please have a look and comment more or less in the same way that I'm doing. So you can see that if I want to you to tell me something about the coupling, there will be zooms. There are integrals. There is a typical one with a depth. Comment on, for instance, the CH2. If there are expansions or zooms, please comment on them. Probably if there are expansions is because it helps you. Okay. We'll finish with advanced retrosynthesis. Once more, I don't want to linger too much on this one because there is a video that explains that. But during the whole course, we saw the systematic retrosynthesis of different functional groups. Remember that you need to use them all at the same time sometimes, depending on the molecule that you are disconnecting. I am pretty sure that you noticed that already on the big workshop question, especially my question, but also Marcella's one. So you might have noticed that there are different ways to do different things. But the good thing about retrosynthesis, I keep telling you, that there is always more than one correct answer. So don't expect that if you do not follow the pattern or the marking scheme that I prepare, you will lose marks. If you do something, and we saw them on the non-assessed workshop, we saw that in class, we discussed, we had fun, we had a good fun sometimes. Try doing a retrosynthesis and a forward synthesis in a way that it was completely not prepared by me. So keep in mind, if your retrosynthesis and synthesis is plausible, even though it's not the one that I propose on the marking scheme at the exam, you will get very good marks, sometimes even hold the marks if the solution is correct. If you take less steps than I do, even better. If you take longer pathways, maybe you wouldn't do that in the lab, but I will accept it if everything is plausible. Remember these general rules. Always count the ring size. That's very important. And remember, I put you all these kind of tables that, once more, I'm telling you, they're far from comprehensive. These are just indications of the most common and recurrent ones, okay? So all these tables, for instance, oxidation reductions, try to remember some numbers on the common pKa's. That's very useful. Oxidation reductions here to get either from alcohol to more oxidized carbonyls or the other way around. These are the most common functional groups that we have seen, but again, it's not comprehensive at all. But if you remember all of them, I am pretty sure that you will have a very good idea on how to proceed during an exercise. Remember that the one that I put you on the big workshop is the level of difficulty and the length is very, very similar to the one that I normally put at the exam on the long questions. Of course, there are going to be some short ones. Carbonyls, we notice, are very, very useful. You saw that also in the, once more, in the retrosynthesis big workshop. Count the relationship between carbonyls. If you have two carbonyls, maybe think about starting from a dicarbonyl, even if you don't have a dicarbonyl in your target molecule. Remember that there are always ways to insert and remove carbonyl groups. Okay, think about the cyclizations. You can use normal cyclizations, or you can use pericyclic reactions like we have seen in this part of the course. Think about always electrodonating groups or electron withdrawing groups, which are on different parts of the molecule. And remember that you might use this cyclization to wrap up or to connect two big blocks of a large retrosynthesis. This is very good, especially for DL solder, because the DL solder works very well independently sometimes on the functional groups that they're around. The only thing that is really dependable on the DL solder is the electron withdrawing group on the dienophile. This is something that has to be done. Remember, when we talk about protecting groups, that especially in retrosynthesis, you don't need to use, or you don't need to tell me, I need to protect this molecule. So you will not lose any marks if you don't mention a protecting group, but you must say that if you're using a protecting group in synthesis. So if there are any regioselectivity or chemoselectivity problems, you need to solve them in synthesis. So remember that if there are too many regioselectivity problems, you probably need to go back to the same target molecule and start disconnecting from a different place. Okay. I think my revision stops here. I wish you very good luck for the exams, and I would like to know if you have any possible questions either on the exams, about the exams, or about any part that I can help you with for this revision. Any questions that you want to ask me? Anyone? If not, allow me once more to tell you very good luck for the exam. Please consider the literature review that you have to do as well. And for me, I will see you next year, basically. And for anything, remember, we can always arrange extra Zoom sessions if you need to revise something particular and I can help you with, or I'm always available by email or normally in my office. If there is nothing more, I will stop the